Now, the solubility in water of carboxylic acids is going to basically follow the same rules as all of the previous ones and all of the following ones, as far as functional groups. Smaller carboxylic acids are soluble because they have these polar regions, and larger ones are not, because what you get with the larger ones are larger alkyl chains. If the chain is really, really long, then you have, let's say there's more carbons in here, they can block water from getting to this polar region, so they become insoluble in water. Now, that being said, carboxylic acids form the basis of fats, but we can make them soluble in water by reacting carboxylic acids with some strong bases, and that's called saponification, which we won't get into, but you may know that soap is really just fat, which are long fatty acid chains, which has carboxylic acid at one end, and then the alkyl chain that can be really long on the other end. All right. So if you do that, if you saponify these fatty acids, it makes it more polar and can actually then dissolve in water. Well, they form soaps at that point, and so it is not impossible to get really long chained carboxylic acids to dissolve in water. You just have to do something to them. This picture here shows you how a carboxylic acid can hydrogen bond with water and therefore dissolve in water. And so this compound there is acetic acid, which clearly dissolves in water because it's vinegar. It comes from wine, fermented wine. And so vinegar is usually about a 5% solution. Acetic acid is also a liquid at room temperature. So you can see the hydrogen bonds here, 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 and there. So it's very extensive, so therefore very soluble. And as a reminder, you have on the water molecules, you have a partial positive on each of the hydrogens. You have a partial negative on the oxygen of the carboxylic acid, partial negatives on the oxygen molecules of water. The hydrogen part of the carboxylic acid is partially positive, partial negative on that oxygen as well. So, I mean, obviously this should make sense, but that's what's going to happen. To reinforce my information there, we can see the solubility of some of these basic carboxylic acids. And so methanoic acid is soluble, ethanoic or acetic acid is soluble, propanoic acid is soluble, butyric acid is soluble, pentanoic acid is soluble, and then you get to hexanoic acid and benzoic acid, each with 6 carbons. Or actually, benzoic has 7, but those are slightly soluble, and then anything bigger than those are going to be insoluble. So another property of carboxylic acids is their acidity, hence why they're called acids. But when you take a carboxylic acid and you dissolve it in water, as seen here, they can dissociate into a carboxylate ion and a hydronium ion. Now this is not extensive. It's only about 1% of these molecules over here are actually going to dissociate. 99% will stay undissociated, and it's actually going to be greater than 99%. So it's not very common, but the fact that it can make any of this is what is responsible for the acidity of these and why vinegar tastes sour. It's because you have a higher concentration in that solution of H3O plus ions. Example 2, write the balanced chemical equation for the dissociation of methanoic acid in water. So, as a reminder, methanoic acid is this, also called formic acid. All right. Write the balanced chemical equation for the dissociation of methanoic acid in water. So we've got water right here. And when that dissolves, you're going to have the hydrogen on the carboxylic acid dissociate, and you're going to get H3O plus. And the name of this would be a methanoate ion. Here you've got the hydronium ion. And then this is methanoic acid. So you can see the methanoate, methanoic acid. Neutralization of carboxylic acid is essentially what I brought up before. You can react hydroxides, so sodium hydroxide and potassium hydroxide, with carboxylic acids. And since you'll have in these solutions, you'll have HO minuses floating around, and you've got these, albeit weak acids, the hydroxide can react with the acid, because again, you're going to have a partial positive on the hydrogen there, or partial negative on the oxygen, but this can attack that, which would actually give the electrons of this bond right in the center there, not shown in the picture, but it'll give it to that, which would actually make it have that full charge. And as a result of these reacting here, you get water. The product of methanoic acid reacting with sodium hydroxide is sodium methanoate, which is used as a de-icing agent. It's used in dyeing materials. It's a buffering agent. There's a lot more uses for that. The bottom one, if you react benzoic acid with potassium hydroxide, you get potassium benzoate, which is a food preservative. Basically, it kills bacteria and mold and things like that. Sodium propanoate, which comes from propanoic acid reacting with sodium hydroxide, is also used as a food preservative. So is sodium benzoate. The other one on the previous slide was potassium benzoate. But we also have this monosodium glutamate, which would come from glutamic acid, which is one of the main amino acids that exists. But we'll get into that in the next unit. Anyways, this is more formally known as MSG. MSG is one of these compounds that people are afraid to ingest, kind of like gluten-free diets, because it's thought to give people headaches and have other problems associated with it. But all actual scientific researches have shown that MSG does nothing to you that would cause any problems. Just kind of like gluten does. Unless you have celiac disease, then you can be allergic to gluten or whatever. No one is sensitive to gluten. They are either allergic to it because they have celiac disease or they're not. And the same thing goes with MSG. In reality, it's a media-driven thing where no one actually has problems with it. It's just, so you see food labels that sometimes say, not with MSG. And usually these are Chinese-type recipes and dishes that say that because it was thought to be the cause of Chinese restaurant syndrome, which gave people headaches. Example 3, what carboxylic acid will produce potassium butanoate when it is neutralized by KOH? I mean, this is almost self-explanatory. Since it's butanoate, it has to be butanoic acid, okay? It doesn't ask for you to draw it or anything, but if you were to, since it's butane derived, it has 4 carbons, and therefore you have butanoic acid or butyric acid.